Welcome everyone to this week's SETI Colloquium. This week we have Daniel Ongehausen from Goddard, who will be giving a talk on sniffing exoplanet atmospheres, understanding their spectra, which will be a very important subject in the year of JWST. Daniel is an NPP from NASA Goddard. He worked with Mark Clampin. I was going to run through his bio, but he tells me his second slide is his bio, so I think I'll skip that. I'll restrict myself merely to making the presentation of the very rare and very prestigious SETI Colloquium mug.
Oh,
so thank you very much.
Thank you
for taking the time to come out and talk with us. And with that, you can take it away.
Yeah. Thanks for the introduction. Thanks for letting me invite myself, basically. So happy to be here. I don't want to go into the details, but I've been around quite a while, always following the money as most of us. And I'm going to talk about how we analyze or how we get a sniff of alien atmospheres using all kinds of different instruments. And that's one of the themes of my career, is just trying new things, trying new instruments, trying new platforms. And but I want to start with a little bit bigger picture. So the question of astrobiology, or if I talk to people about astrobiology and they ask me, what is that? Actually, I think it's a word that was born here, kind of, right? Wasn't it? Ames thing, astrobiology. Anyway, so I always start with the story of the blind man and the elephant. So it's like an old Indian or Thai, I guess, legend where like 3, 4, 5 blind men find an elephant and want to figure out what is that elephant. And the first guy is touching the back and he's like, for me that feels like a brush or something. The second guy is touching the leg and he's like, I don't know what you're seeing, but for me that's more like a tree or something like that. The third guy touches the side and it's like, that's like a stone if you ask me, or a big rock. And the second guy touches the front and he's like, yeah, for me that's neither a rock nor a tree nor a brush or anything. And that's kind of how it goes in astrobiology. So we are all in our separate fields, kind of blind, kind of not really connected with the others. And if you want to understand that whole question of life in the universe, we really have to zoom out, stop using our lingo, and really connect these different fields, just as these blind men have to connect the different dots to understand that elephant. And I'm going to come back to this somewhat later in the talk. And I want to focus mostly on this astrophysics part, on exoplanets, which is the work that I'm mostly involved in. And actually want to point out that it's a really old question. Even though we found the first exoplanet 20 years ago, it's almost 3,000 years ago that Epicurus started asking that question. And then other really great minds like Bruno or Newton thought about the idea that there are other worlds that are similar or maybe not similar to ours. How many are there? And only one of them got killed for that idea. So it's one of those 3 that's not too bad. And it still took 300 years or 350 years after Newton that we start slowly but surely to figuring out these questions with, first of all, stopping killing people for thinking about that, and with improved technology, we got to a point where we started to answer these questions. And then probably most of you are aware that we got like the best, even never expected answers to these questions. We even got amateurs discovering with planet hunters, for example, exoplanets. We find exoplanets, or in this case, maybe it's not real, we're still thinking about that one. In our closest neighborhood, we find planets that are potentially habitable. Or basically you guys at Kepler, you basically double the number of planets that we know every year. We find really crazy ones, like that Saturn on steroids, like a ring planet with like a huge ring. And we find planets around stars that we thought are way too old to even have planets. So we are really starting to answer these old questions. And that's what makes me, on one hand, humble that I'm living at the right time to use the instruments to be answering these questions, and also kind of proud that I'm answering the question that these great minds, thought about for centuries. So being part of the community that answers that really old question is one of the drivers for me. And we are so successful with finding these exoplanets, mostly due to Kepler, but also with other detection methods, that we can start putting them in some sort of statistical context, and in this case, in a periodic table. So it's really just the size, so from Mercury size towards Jupiter size, and then just in 3 basic distance or temperature zones. So the hot zone, too hot for life, warm enough, that habitable zone, and then too cold for life, basically. And what you can see is there's a huge crowd up here. That's mostly an observational bias. So this doesn't reflect the overall occurrence rates. This is mostly an observational bias. Obviously, it's easier to find big ones closer in because they have bigger transits, they have a stronger ray velocity signal. So this whole trend is mostly observational bias, and with improving technology, we're pushing these boundaries farther and farther to the colder and smaller planets. Another interesting thing is if you compare this to our solar system, so same plot, but with all the bodies from our solar system in there, you see it's really different. So we have all these rocky planets, somewhat close in, our gas and ice giants somewhat farther out, and this was a picture in planetary planet formation before we found the first exoplanet. We thought this is how solar systems look like, and if you go back to the plot of the exoplanets, maybe it's not how solar systems look like. So we find many of these close-in gas giants, which we don't know how they got there. We find these super Terrans, these mini Neptune super Earth planets, which we don't even have an analog in our solar system. Maybe Planet 9 is one of these. But this is almost the biggest group of planets we find, and we don't have any analog to them. So it seems like we are finding stuff that's really different from what we have in our solar system, and that each of these planets are worth finding out about these hot Jupiters, about these super Earths. So these are really big questions right now that we have to answer before we maybe move on to the more habitable ones here. Then the question is, why is it so difficult? Why did it take us 3,000 years to start answering that question? And the basic, very trivial answer is stars are bigger than planets and stars are brighter than planets. I'm not sure if you can even see that. So this little dot here is Mercury. So this was the Mercury transit just 2 or 3 weeks ago. And this is a challenge that we have to work with. I mean, admittedly, that's the smallest planet by definition that we have, but it's still like a tiny, tiny little dot in comparison to that huge, noisy, sometimes active host star. So the techniques we use are either indirect methods, so the star is doing something that makes us conclude that there's a star, or we need more like brute force methods, canceling out the stellar light. That's what the chronography folks do, just pushing until we push down the stellar contribution to the 10 to the 10 contrast ratios to actually separate these planetary fluxes from the stellar fluxes. And the technique that I mostly use is actually similar to this one, or in principle the same. We're looking for transits and these photometric changes when the planets cross around the stars. And that's what we call differential photometry. So for some systems, we are lucky enough that we look edge on the system, and in most cases, we got these primary transits where the planet moves in front of the stellar disk and the light drops a little bit. Then it does that whole orbit around here, and then, depending on the geometry, in most cases, it also disappears behind the star. And if you look at the differences between these phases, or in the change of the stellar light, we can reveal information about the planet. And this is how typically a light curve like that looks like. That was the first, or maybe the second, half-orbit light curve, in this case of HD 1 at night, 733b, one of the benchmark gold standard hot Jupiters, one of the first transiting exoplanets we found. And this was observed at 8 microns, so somewhere in the infrared with the Spitzer Space Telescope by Heather Knudsen. And you can see here, this first big dip, this is the primary transit, so about, in this case, 3%, basically the area ratio between planet and star. And then you got this long baseline here, which is why the planet is moving around here. And then you got this somewhat smaller secondary eclipse, basically the ratio of the fluxes you get from the star and the planet. And in this case, roughly a factor of 10 for this hot Jupiter, factor of 10 smaller than the primary eclipse. But there's more to it. So this, what looks like a straight line here, if you zoom into it, you can actually see this sinusoidal shape on top of that phase curve. And that's what we call it, orbital phase curves. So you can basically see the day side of the planet moving towards us over the orbit. So right after primary eclipse, you see the dark night side of the planet facing us, and then over the orbit, the day side is moving towards us and slightly increasing that signal of the phase curve. And we can draw a lot of information just from that curve. We can get day sides, night sides by comparing that bottom here, which is basically the night side, towards that bottom here, which is the contribution by the day side. Another thing we can see here is that brightest spot is slightly shifted from the secondary eclipse. So if our hottest part, or the brightest part of the planet was right in the center of it on the substellar point, we would expect this to be right in the secondary eclipse. But because this bright spot or this peak of the phase curve happens before the secondary eclipse, we can conclude that that hot spot is slightly shifted from the substellar point. So there must be some sort of winds maybe that transport that hot spot towards the side. So in a sense, we can actually map exoplanets in a really crude way, but we can map the energy distribution on these exoplanet surfaces with these observations. And that's actually the first thing that I worked on. So I was working at RPI in Troy, upstate New York, and this project actually won an undergraduate research prize, and we went to Capitol Hill, me and my student Emdel Arm, and what we did was taking these secondary eclipses. So all these little dips here are secondary eclipses, so when the planet disappears behind the star in the Kepler data set, and also these phase curves, and fitted the secondary eclipse and phase curves, and long story short, we were able to go for about 20 planets, derive their brightness temperatures, their albedos, and the night side temperatures. And at that time, that was, I think, one of the papers with the largest group of consistently and comprehensively derived parameters. And then we also, obviously, if you get a statistically meaningful sample, you also try to find some correlations. In this case, there's a lot in this. So this is the albedo on this side versus the incoming flux. So people thought maybe if they are highly irradiated, they become more reflective, or the other way around. Then we also have the log G of the host star and the metallicity of the host star, and you can't really see any correlation in here. So if there was anything, any of these parameters changing the albedo, there would be some sort of correlation in here. The only thing we can say, they are really dark or really low in albedo in comparison to Jupiter. So Jupiter has an albedo of 0.5, and all these hot Jupiters are down here. So it's kind of counterintuitive, right? One would expect if they are so close and if they are highly irradiated, there might be like white glowing or something, but they're actually charcoal. So these hot Jupiters, at least in the optical, in the Kepler bands, are pretty dark or pretty low in reflectivity. So that was the first thing in phase curves. Then another work was also when I was in upstate New York with Ben Plesek, who's now starting at Wentworth as a professor this fall. I was partly supervising his PhD work, and he built a Bayesian phase curve modeling and retrieval tool called ExoNest. All these phase curves, you can imagine there are tons of parameters that going in, and many of them are highly degenerate. So for example, these secondary eclipses, albedo, so the reflected light and the emitted light are really highly degenerate, and you really need Bayesian methods to decorrelate that and to visualize these degeneracies. And this is just one example. The phase curve models made with ExoNest, and in this case we could first of all prove a planet without the transit. So really just from the phase curve you can confirm the planet from the Kepler data, and we could even confirm that it's an eccentric planet. So it's an eccentric versus non-eccentric model. And this is just one example. So we have about 3 or 4 papers just using that ExoNest code. One with John, where we looked at a certain Kepler candidate. So it's a really great tool, and we also applied it already for combination of TESS and Kepler data. We just started to also apply that code to gravitational microlensing data that might be coming up from Kepler. So it's a really nice and really nice tool, that code, and really versatile. So this is another thing on phase curves. Then another application of phase curves, so we are still only talking about Kepler here, is looking for exotrojans. So I was living in upstate New York, in Troy, and there's so many Trojans around me in Troy. I thought about, what about maybe there are some Trojans in the Kepler data. So for those of you, just a quick recap. So if you have a star-planet system, you got 4 gravitational stable Lagrange points, and in 2 of them, L4 and L5, they basically act like a gravitational trap. So everything that's floating around eventually ends up there. So it's kind of like a cosmic trash can. And so all of this stuff, eventually all that left over from the planetary formation process ends up in these Lagrange points and builds these clouds of so-called Trojans. And the cool thing about these Trojans is they always appear at the same phase. So even if you have a 60-day orbit or a 600-day orbit, they always should be at the same orbital phase. And that was the idea that we had. So if you look at planets and look for them, or look for Trojans in the Kepler data set, they should always appear at the same point of time. So if you have the big transit here in the center, they should always appear in transit here and there. But obviously these signals are super small, so we're talking about parts per million, so you probably won't see it in a single system. So our idea was, what if we put all the Kepler data on top of each other? And that's kind of, so there's a little bit more to that paper, so I refer you to look at the paper. There are a couple of more statistical tests that we did. But in principle, what we did, we folded all, or almost all Kepler planets, 4,000 planets with 90,000 phase curves on top of each other. And then eventually, the statistically significant dips at the L4 and L5 popped out. So if you really compress the whole Kepler data set, funnel it, and get one plot out of all phase curves on top of each other, you get these little dips in the L4 and L5 points. And you can see here, this is ppm flux, so we're really talking 2-3 parts per million here, that these dips maybe caused by Trojans are deep. The thing is, that's only like a 2-3 sigma detection, so we didn't want to lean out of the window too far and call it a detection, so we call it evidence for exotrojans. As I mentioned, there are a couple of other tests. One test we did, for example, is if you see a dip in L4, or if you see a dip anywhere in the light curve, is there a correlated dip at another point? And the only correlation is between L4 and L5. So if you see a dip in L4, there's also highly likely a dip in L5. But there's no other phase, so there's not, if you see a dip at point 1, you don't see a dip at point 7. So the only correlation is really between these 2 points. So there are a couple of statistical tests. And actually for that paper, we got an extra statistical referee that had to look at the paper. So we are quite confident that at least our methods were fine. So, but we still didn't call it a detection, just evidence for these exotrojans. And I mean, the shape makes sense, the size kind of makes sense. So the depth of these tiny transits refer to something like Ganymede size. So one body the size of Ganymede, or 1 million bodies with a kilometer size diameter. So this is kind of like the same ballpark as Jupiter. So it smells like Trojans, it sounds like Trojans, so it might actually be Trojans, but we didn't want to call it an actual detection. Okay, so all the stuff I showed so far was Kepler data. So really just one color in the Kepler band. But of course, it's much more interesting, so you get a whole dimension, more of information if you do these observations spectroscopically. So that's what we call spectrophotometry, because you can either go from a spectroscopic instrument and bin down, or you can use, as in this case, a couple of photometric channels at the same time and observe these transits or eclipses. And then you can do this again in primary eclipse, where you probe the terminator. So while the planet is moving in front of the star, you got this thin layer, mostly of the upper atmosphere, the terminator region of the planet, absorbing light during the transit. And then if you have something that absorbs, your planet appears bigger, so you get a deeper transit. And if there's nothing that absorbs in the atmosphere, your transit is somewhat shallower. And these spectral features are of the order of 10 to the minus 4 for these on Jupiter. So the absorption of, let's say, methane in the terminator gives a 10 to the minus 4 shallower transit or deeper transit than the continuum. Then the same observation you can do in secondary eclipse, when the planet disappears behind the star. There, the light that's missing during that eclipse is mostly the emitting day side of the planet. So you can observe that high up in the air, low pressure outer terminator, and then somewhat deeper pressures inside of the planet with these secondary eclipses, and get a quite nice picture, rough idea of what's going on in these exoplanets. And interestingly enough, so the broadband depth, so the secondary eclipse is about a factor 10 smaller or less deep than the primary transits, but the spectral features, so an emission line versus the continuum, are again on the 10 to the minus 4 level. So that's the signal to noise is still high. 10 to the minus 4 for Jupiter is quite a challenge, but it's the same for primary and secondary eclipses. So that's also somewhat counterintuitive, because people usually think these secondary eclipses are much harder, but the signal to noise we have to go if we don't want to do spectroscopy is pretty much the same. Okay, so how does that work? Really short explanation how we get to the spectra. So then each of these transit or eclipse light curves represent the spectral value at at that wavelength. So in this case, an observation with Hubble NICMOS in 2009 when I was working at JPL with Max Main. So that's the day side of HD 209, another hot Jupiter, benchmark hot Jupiter, and then each of these black crosses here represent the secondary eclipse light curve depths at that wavelength. And then at that time in 2009, we got away with just forward modeling. So we called our colleagues, in this case Giovanna Tinetti in London, to model these atmospheres. So she put in a water atmosphere that didn't fit at all, then added some methane to the mixture, and we got this green model that kind of fit the data, but still not really good enough. And just as we added methane and CO2 to the mixture, we got a spectrum that kind of fit our data. And this is what we did in 2009, so really just forward modeling comparison. But this whole comparison, that whole spectral retrieval became like a huge field. So I could give like at least 2 other talks just about these retrieval of composition of temperature and pressure profiles just from these spectra. So this, what I just call comparison here, is really, really a tricky business, and also involves mostly these Bayesian methods that I mentioned before. So just as a warning, that's not just forward modeling that we do with these spectra. Okay, so then the question is, what can we do right now? So as I mentioned before, these hot Jupiters are the easy ones. They are relatively hot, so they are kind of bright in the wavelengths we observe. They are big. They have a huge signal on the planet, higher contrast ratios, and the questions we are able to answer right now is: are there any interactions? Is a host star blowing away material from the planet? How does that whole day-night side heat exchange work? Since most of them are tidally locked, they got a super hot day side and a super cold night side, and we don't really understand in which cases the heat gets transported from the hot side to the night side. So all these questions we are able to tackle with the instruments we have right now. And one, from my perspective, the best observation we ever had from Hubble is this phase-resolved emission spectrum of WASP-43. So WASP-43, one of the hottest and therefore highest contrast hot Jupiters. This is not work by me, this is work by Kevin Stevenson. So they observed 61 orbits with Hubble, so quite a huge chunk of time they needed with wide field camera 3 over a couple of orbits of WASP-43, and then were able to, first of all, derive that emission spectrum at different phases. So it goes, so this is like the day side, going up to the day side here, and then going back to the night side. This is the night side, so you can see this water absorption feature depending on the phase. Then also thermal profiles depending on the phase. So you don't really have an inversion anyway. So if you go to the day side, there might be a tiny inversion, and then they also got these brightness temperatures maps that I mentioned before, that from these phase curves and the shifts in the phase curve, we can also derive some crude first-order maps of the heat distribution of the surfaces. And this is really just a glimpse at what's possible in the future. So we probably can do similar stuff with James Webb on colder planets, on somewhat smaller planets. So this is really just a first glimpse at what's going to be possible in the future. And that's why I like this animation and showing this picture. This is really the first time that someone opened the door to sneak peek what's going to be cool in exoplanet photometry in the next couple of years. Another question, as I mentioned before, this whole super Earth versus mini Neptune, these intermediate-sized planets that we don't have an analog in our solar system for, that's also a question we slowly but surely are able to tackle with the current instrumentation. So figure out where's the transition region, at what size does the rocky planet become an ice giant. So all these questions are also in reach. And then obviously the big question, going back to the guys in the beginning, answering the big question, is there life out there? Can we eventually use this technique of transit spectroscopy to find these fingerprints of life, what we call biomarkers? And right now, the most promising, at least for life as we know it, is if we find oxygen and methane at the same time. And there's a nice analogy that I got from one of my colleagues. It's like grad students and pizza. So if you have both in the same room at the same time, there has to be someone has to bring the pizza. There has to be Papa John bringing pizza because these grad students eat the pizza all the time. And that's the same for oxygen and methane. If you put both in the same room, they can't exist. They just eat each other off. So you either have something producing oxygen or something producing methane, and that's most probably going to be life. So this is the grad students and pizza comparison to oxygen and methane, why we think these are pretty good biomarkers. And but the big problem for this is actually that the atmosphere is not just the biosphere. So we got all this, we got volcanism, we got northern lights, we got all these different processes that contribute to the atmosphere. And that's really one of these elephants that I mentioned in the beginning. So figuring out what is a smoking gun for life, what is a real biomarker, really needs atmospheric chemistry, needs climate modelers, needs geologists. So this is a really a question that we can only tackle as the whole astrobiology community with input from all the other fields. And then usually they tell us, yeah, we find this tiny little signature, and we're like, yeah, we can't really observe that with our telescope, so we have to iterate that. So that's one of the big questions that many people figure out right now, also because we want to build the next mission, like HABEX, LUVA, all these potential life finder missions, and we have to define that now. We have to find biomarkers and define the sensitivities to build these telescopes. So we can't wait to define these biomarkers in 20 years when we have the missions, but we have to define them now to give the mission design an input, what we're looking for. Okay, going back from the future, back to the past, how I started, and from space back to the ground. I actually started my career trying all this awesome observations from the ground, and looking back, it obviously failed. So as you know, it's usually much cheaper, even with these awesome telescopes in Hawaii and Chile, it's still much cheaper and much easier to get time on them than from space. And usually you also have access to bigger dishes, so you can get higher sensitivities. You usually have better resolution instruments. So there are a couple of advantages if you could transport that technique from space to the ground. On the other hand, there's obviously our atmosphere killing stuff. Then you got weather and all these other problems from the ground. So it was really not trivial to do these observations, these awesome observations with Kepler, Spitzer, HSD from space, also on the ground. There were a couple of observations that worked, a couple didn't work out, but we never really found a workhorse that does similar awesome observations from the ground continuously or repeatedly. And it's only the last couple of years that we got 2 new instruments that might, at least in the infrared or in the near-infrared, that might close that gap. One is MOSFire at Keck, an instrument that I observed a couple of times with. It basically works with a huge slit mask. So you can, so this is in the optical path. You can build completely arbitrary slit mask. In this case, you got these tiny little holes here where you can put a star in each of these holes and get a spectrum for each of the stars. But you can, in principle, also take all these registered and make a pure imager out of that. And what we use for our observations is basically making a long and wide slit. So like a 12 arc second, 30, 15 arc second wide slit where we put our transiting host star and a comparison star in the slit, because we figured out in our early observations that slit losses, so that tiny little wiggle of our star in the slit already kills our 10 to the minus 4 signal to noise. And we can also compare, so we can put a comparison star in the same slit, so we can compare for the correcting the atmosphere, and we avoid these slit losses. So that's why we think this MOSFire at Keck might be a great instrument to do these observations also from the ground. Another even more complicated instrument is KMOS at the VLT. That's not just a multi-object spectroscope, it's actually a multi-object integral field unit. So you got these, it's a huge thing. It's like it's more than a school bus sized instrument. You got these 24 tiny arms that you can put into your field of view, and then each of these tiny arms has a mirror on the tip that reflects your star that is in that aperture on an integral field unit. So you get a data cube for each of these stars. So you basically get a 3D image plus a spectrum into the wall for each of these objects in your field of view. And I got a science verification proposal accepted in 2013 that didn't really work out because there were technical issues, as there's usually when you do science verification. Then I got 2 nights in 2014. I went to the Atacama Desert, and maybe some of you remember that picture when suddenly all the flowers bloomed in the Atacama Desert because it rained for the first time in 3 years. That was the night that I observed. So got 1 night in the Atacama Desert, and then it's the night in 5 years where it rained. So all the technicians and engineers were taking selfies because it was so rare that it rains at Paranal, and unfortunately it was the night that I was there. The second night we had bad wind speeds, so I could technically point anywhere at the sky but where my object was, just because the high wind was coming from that direction. So didn't work out in 2015. And then I went again last year in 2015, but the moment I got off the plane in Chile, I got a call that they had a power failure and they couldn't get my instrument cold enough for my observation. So I just spent a week in Santiago watching the Copa America and couldn't observe. But then I went home, and then they finally, so in the 6th try or 5th try, they finally got an observation that worked. And we are currently reducing the data, and it looks promising. So I don't want to promise too much, but maybe just stay tuned for that. So it's tricky from the ground. That's basically the take-home message here. What seems to be relatively easy from space is really a pain from the ground. But I still think we need to push it, because we can take a lot of pressure off James Webb if we can take at least some of these observations from the ground. Also in terms of pre-vetting our targets for James Webb, I think ground-based is still important to do. So the thing is, if it doesn't work from the ground, but works from space, why not go on a plane, right? So you probably all know Sophia here. It's a telescope on a plane. I'm not sure if you can read this. So enough is enough. I had it with these ground-based observations. So yeah, why not putting a telescope on a plane? And this is also a thing that I pushed for quite a while when I was graduating from the German Sophia Institute. So I've been connected to Sophia for quite a while. I don't think I have to introduce Sophia too much here, because most of you should know about Sophia. So it's that awesome 2.5 meter telescope on a 747. It's a German US joint venture. It's observing slightly higher altitudes than commercial airplanes. The first generation of instruments is 7 imagers and spectra, basically covering everything from the optical to the sub-millimeter range. It's supposed to operate for 20 years with about 120 nights per year. A couple of milestones. In April 2007 was the first flight of the observatory, which was tricky enough to put the 16-ton telescope on the back of a plane instead of 300 sacks of water that usually are on a plane like this. Then December 2009, the first open door flight. That's, I think, the video that's shown here, at least the first flight where they opened the door fully. And then in May 2010, the first light observation, and then since 2011, it's in operational science operations. So you can basically propose for observations just like any other telescope. Unless you're German, then you can only propose in Germany, but in principle it's like all other telescopes. It's GO time, so you can apply for time on Sophia. There are a couple of advantages for these transit observations, at least in theory. It's operating in the wide wavelengths regime, so where all this funky photochemistry happens that we're interested in. It's a mobile platform, so you can imagine these transits don't happen every day, and then sometimes you only got 1 transit a year, and that happens coincidentally just observable from somewhere in the Southern Pacific. So with Sophia as a mobile platform, in theory, you can go where these rare transits happen. Obviously, it has less atmosphere, so one of the main reasons why Sophia is built. So we got less total absorption, but also less variability. Because we observe time series, also the variability of the atmosphere that's much lower up there is important for us. And then the other cool thing about Sophia, it's you can put dedicated instrumentation on it. So not like Hubble, where you have to send like a super dangerous, expensive space shuttle mission with astronauts. You have to train for years to just exchange an instrument. Sophia, in that sense, is a space telescope that comes home every morning. You push it in the hangar and put on the newest instrumentation, the latest detectors, the coolest spectrographs you can get. So that's really great advantage of Sophia over space-based telescopes. And after pushing that for a time, we actually got our first exoplanet observation. Here you can see maybe it's a little bit too dark, but the exoplanet hunter team. So we got Eric Becklin, Ian McLean, Ted Dunham, so a couple of really important people in the field that were helping us with that observation, and it was on October 1st, 2013. So I think many of you are federal contractors or working for the government. So do you remember what happened October 1st, 2013? Shutdown, right? So actually our flight was scheduled to leave at 8:55, so 5 minutes before midnight in Washington, so that we could leave in time before the shutdown. If the flight plan was, made so that we start at 9:05, we probably would have stayed on ground. So we left Palmdale, got into air, and then 10 minutes into the air, the pilot said, yeah, by the way, we don't have a government anymore. And then we flew up to Canada. So we flew up to Canada, turned around, and returned to Palmdale. And while we were in Canadian airspace, we were kind of joking, maybe we should go down and ask for scientific asylum for a while or something like that. So that was October 1st. And we had a couple of technical problems that night, but we actually got a transit. So unfortunately, in the beginning, our instrument was not really working as we wanted, or a couple of instruments we used, but we were able to point at our star about 10 minutes before transit, and this is the really nice transit light curve we got from SOFIA. And this is really raw data. This is what I call absolute photometry, so we don't need a comparison star, as you usually, people who do variable stars from the ground always need a comparison star. Even Kepler, in a sense, needs comparison stars with the CBVs that you use. So this is really just putting an aperture around our host star, PSF, and just extracting the data. So this is actually a proof that we are operating somewhere in a space-based environment, because these observations without a comparison stars are really only possible from the ground. So this was the first proof that SOFIA as a platform actually gives us space-based quality data. And if you keep in mind that we're observing a difference here, so we're observing A minus B, so out of transit versus transit. So we really limited by only 10 minutes before and after transit. So this is also something to keep in mind. But even with that kind of like not optimal data, if you compare that to previous observations with Hubble or Spitzer, here color-coded, SOFIA at least gets close to that. So within 2 or 3 times the sensitivity, and again, remember first time you used it, really limited observing time, we got down to about 1.5 times the photon noise, and sensitivities of 180, 160 ppm. So again, a proof that SOFIA could play as a platform, could play in that league with these space-based platforms. That's another observation, a transit of GJ 3740b, a warm Uranus, that we observed with a Paschen alpha filter of SOFIA in the flight with a flight cam infrared instrument, and in another channel in the I band with FBI. And this is also one unique thing for SOFIA, that you can use the beam splitter and observe in the optical and the infrared at the same time. I'm not sure yet if there's anything from the ground. Definitely nothing that can observe at space quality at these wavelengths parallelly. And this is the flight path we took. So we flew out of Palmdale, got up here, similar actually to that October observation that I meant, went up here to Canada, and then back here. And the thing you can see here is, when we return in the morning, you can see the morning come. So you can see the sunrise here, right? And one of the constraints with SOFIA is that we have to land before sunrise. So NASA is scared that we pointed at the sun, and then we cannot close our door, and then sun falls into the telescope, and hell is going to break out on the plane. So that's why we are constrained. And the problem in this case was our transit just ended 10 minutes before sunrise. So we really had to come back right after the transit observation to be in Palmdale before the sun is up. And this is actually one of the problems with SOFIA in practice. So this whole flight planning is a really huge constraint for these transit observations, even though in principle it's a mobile platform and we could go where the best environment for these transit observation is. All these constraints, there are also a couple of, actually quite many military zones here that SOFIA can fly through, and the constraints to come back and start and land in Palmdale and to come back before sunrise. This really actually makes it hard to find perfect conditions or a perfect flight plan to suit these exoplanet transit observations. Another that's more general problem for us for us transit observers in general is that the instruments are not well suited. You can imagine if someone builds an astronomical instrument, you usually build it to take long-term exposures of something faint, right? You look at a faint galaxy for 15 minutes to get your signal to noise, and then you point at the next target. But our targets are actually super bright, and we only do a couple of snapshot observations, but have to be stable over time. So this really has different requirements to the instrument than standard astronomical observations. So this is why we in general have problems using standard instruments. For example, when I go to Keck, I usually ask them to defocus, just so that we can spread our signal a little bit more over the detector, that we can use longer integration times on these bright targets. And obviously people are crazy. I mean, we don't build a 10-meter telescope and then you come and defocus it. So that's a general, not just the Sophia problem, it's just a general problem for the observations we do. And then obviously there's a lot of competition with the mid and far infrared, where Sophia is really unique and really the only platform available for the whole community. So we really have to compete with our science cases, which these science cases that totally rely on Sophia, because there's no Herschel, there's, as far as I know, no mid or far infrared space mission plan. So this is why Sophia in practice has some constraints for these observations. And I mean, it's clear that Sophia was never supposed to be any kind of survey mission. So just because of the limits in time and the instrumentation that cycles through. But I think there are a couple of unique science cases that really only work with Sophia, and I keep on applying with them, and hopefully we get some time again. And these two papers are also in the making, so maybe once they are out, we got a little bit more arguments to keep observing with Sophia. Okay, finishing up here, looking forward. Most of you might have heard about the Swiss or European Cheops mission coming up, then obviously TESS coming and James Webb coming. So the future is really bright for exoplanet transit observations. So we got 3 missions or 2 missions completely dedicated to it, and a huge part of James Webb also hopefully dedicated to exoplanet transit observations. So there's a lot of cool stuff going on here, and I don't want to, that's again another talk. One thing that I want to point out though is that one of the most important things we have to do in the next 2, 3, 4 years is to organize the traffic. So the Cheops and TESS mission are really, really close to each other. So the first data release from TESS probably is around the same time. You have to put the first targets into the James Webb pipeline. So what's really important for us is to do that whole follow-up work and kind of organize the traffic. So like the interesting super Earths, we put them on the fast lane, and the boring hot Jupiters, we maybe put them, on the detour. And it's really important because we only have limited time with James Webb, and we might just get a shot at one super Earth, and then the question is, when do we pull our trigger? Do we wait until the end of TESS to find our perfect target, or do we wait half of the lifetime of TESS to go at a not so good target? And if you only get time for 10 hot Jupiters, which are the 10 you choose out of the 100 we have? So this is really questions we have to answer now and not wait for James Webb to come. And to summarize this, so this is like a summary slide taken from George Ricker's TESS talk. So this is realistically the questions we can answer with James Webb. So there are some people who think we might be eventually able to get the first signs of habitability for some wet super Earths, but realistically, we should be able to close that whole hot Jupiter topic. How does that heat, day-night side redistribution thing work? How do inversions work in these atmospheres? And also, how do they form in the first place? We don't really know how these hot guys got so close into their host stars. So I think realistically we can close that chapter or really get big answers in these, and maybe point at a couple of at these wet hot super Earths. But realistically, unless we get really, really lucky, we probably won't get biomarkers with James Webb. And but it's still it sounds a little bit disappointed, but I'm still excited to observe with James Webb and answer all these questions. And that's basically the end of my talk. I usually have this a video of the 2 of my Sophia observations. So I took my little GoPro camera on the plane and just put it in certain corners while we were observing. And usually I just let that video run while we do some question and answers. So thank you.
All right, thank you very much, Daniel. Before I open it up for questions, I remind you we are being recorded. This will all show up on YouTube, but most importantly, stick up your hand, wait until the microphone gets to you so people online will be able to hear what you're asking.
Thank you. That was really cool. Given the limits you have in observation times and tools to observe with, have you or one of your colleagues looked at the spectral signature of that wacky WTF star with the 22% dip? And if so, what kind of information could you glean from looking at the spectral changes?
Yeah, I made the mistake to actually work on this planet, and then we got a lot of press. So, okay, where do I start with this planet? It's like such a huge topic. So I think it's great. It's great that we got this planet and got the public interested in it. It might become a little bit more dangerous in the future. You know, if you want to ask for money for HABEX in 10 years, and then people said, wait, you found that alien megastructure 10 years ago. Why do you need money for HABEX? You know, I mean, you know, we just have to make sure that we don't start to become, you know, Vato on Mars or Voyager left the solar system kind of guys.
Yeah, what's your typical alien megastructure spectral, profile look like?
I mean, don't get me wrong. I think it shouldn't be a taboo to think about it. That's totally, and I think the coolest message here is that we actually, and that goes back to that question, or the questions I showed in the beginning, that we are the first generation that actually has the instrument to eventually answer that question. Even if we don't find an alien megastructure, we have the instruments to do that in the first time of human history, and that's the biggest message here. And if it engages the public, I mean, it's a good thing, right? So.
Yeah, but can you find out what it really is? Can you find out what it really is with spectral analysis?
I mean, hopefully already with follow-up photometry, but with James Webb, we definitely get a bigger picture of the infrared axis. I think that's the biggest question right now. If there's anything, even if there were alien megastructure, they have to re-radiate whatever they are doing in the infrared, and obviously, or apparently, there is none of that. So we definitely could get a better grip of that IR question for that star. So yeah, James Webb is going to help with everything. So yeah.
Any other questions?
Yeah, I was fascinated by your result on extrasolar Trojans, and I was wondering if you could say anything more about the possible distribution of objects or anything like that.
So first of all, it was, as you've seen, it was a really small signature even for the whole sample. So in the first version of our paper, we tried to look at you know, certain distances, for example. But if you only get a 2 sigma detection on the whole sample, you don't really want to cut it in smaller boxes. So we did that in the first version, and that extra statistical referee we got said, you know, take it out again. And the first thing, so there's actually more to that paper, and I can explain that now that you asked. So in the beginning, we took all Kepler planets and didn't put all of them on top of each other. So really from the short distances where we wouldn't even expect Trojans because of stability reasons to the really long distances. And for them, we found an upper limit of about 1, so we call it a occulting area analog. So something like one object that would have 450 kilometer diameter. So that's the upper limit for the whole sample. And what we did then, we did a statistical test. So if we see a dip in L4, we also see a dip in L5. So what we did then was, for every exoplanet or for every Kepler planet, we found a dip in L5. We took the second half of the light curve. And for everyone we found a dip in L5, we took the first half of the light curve and then put all of these together. And for these, we found these tiny little dips, which are analog, which are, as I mentioned, to one object of 1,000 kilometer diameter or 1 million objects of a kilometer size. And that's kind of like the same ballpark as Jupiter. And also the shape you have seen, maybe you have seen this shape, is more like almond shape. It's not like a deep dip. So there's also like the distribution you would assume for Trojans in these, you know, elongated orbits around L2. So as I said, you know, it all smells like Trojans, sounds like Trojans. So, and it's not like a super crazy claim. It's not like an alien megastructure, right? So we have Trojans everywhere in our solar system. So it's kind of like expected to also see them out there. So, yeah. Does it answer your question?
What kind of features would you like to see in a perfect SOFIA instrument for the work that you do?
We actually submitted one to the first call of for extra instruments. So that was a study called Nimbus, and I really liked the idea. So that was the multi-imager. So it had like a couple of dichroics, and you had like 8 fields of view. So you got like 8 photometric channels at the same time, and these channels were chosen that they fit right in these windows you can't observe from the ground. So right between H and K, between K and M. So you got like 8 channels that are completely complementary to what's done from the ground, and it's like all imagers, so that it's kind of like easier to reduce. So you get like 8 channel photometry at the same time. So this was an instrument we actually submitted to the first call of instruments, but now we are getting too close to James Webb that it's probably not really makes sense to put like a dedicated instrument on Sophia, but maybe something like that on a balloon. So I know that people are also thinking about a dedicated exoplanet balloon to do some of that stuff, to get pressure off of James Webb and to do this whole vetting thing before James Webb to characterize which are the best objects for James Webb. So, yeah.
All right, if there's no more questions, I'd like to thank the speaker again and look forward to seeing you all next week.